So we've got our insert into our heap, and now we want to take a look at the ways that we can remove a value from the heap. Removing a value should remove the largest value in this case, since we're creating a max heap. So it's going to remove the top of the heap, or the leftmost value inside of our heap list, right? The trick with deleting a value is what happens after we delete it. The idea is that we need to figure out what replaces the value that used to be at the top of the tree, so like the root of the actual tree itself. And you have a number of different candidates that you could really pick, right? There's a left and right child to that node, and if we were looking at a binary search tree, we might pick out like the min of the right of the node, right? But with the heap, we actually take a slightly different approach. What we do is we say instead, take the value that is at the end of the tree, so the value that was last inserted, and place that to the top. And then what we're going to do is we're going to take that value at the top, and we're going to move it around until it ends up in the right place, and the largest value ends up at the top of the heap again. That is what we would call a heapified down. So let's take a look at what that looks like. What we do is we start off by basically checking to see if the length of the heap is greater than 0, right? So if it's equal to 0, well, we won't do anything. We'll just return none, or we could raise an exception. Doesn't really matter. And then what we do in the else case where there is something to remove is we first store the value that's at the top of the heap as the max value. We're then going to update the heap top to be equal to the value that's at the end of the heap, which would be the value at the -1 index. After this, we do a self.heap.pop, so we remove that value. And then we do what we call a heapify down, right? And we're going to heapify down with the top of the heap. So basically what we did was we swapped the top and bottom of the heap. We removed that maximum value, the value that we had swapped. And then we actually do our heapify in order to maintain the heap property. And just like before I forget, after all of this, we want to return back that max value as a result, right? The heapify down is a bit more complicated than heapify up. And basically what a heapify down is going to end up doing is it takes in the index of the thing that we need to adjust, and then it finds what's to the left and right of it. So we want to find the value to the left of our starting point and the value to the right of our starting point. And then what I'm going to do is I'm going to check to see, well, first off, make sure that the left is less than or equal to the length of self.heap. And I want to make sure that the value at self.heap at L, I want to check to see if it's greater than the value at the current top. If it is, that becomes the largest value that we've seen. Otherwise, the largest value will be the value that we've started at. Okay? And then we're going to do the exact same comparison again. We're going to say if r is less than or equal to the length of self.heap minus 1, and self.heap at r is greater than self.heap at I, then again the largest equals r. We don't need an else in this case because we've already basically covered this case. It's basically either going to be L, I, or R. We want to figure out which one is the biggest of the different options that we have. And then what we say is if the largest doesn't equal I, so the value that we started with, then we're going to do a swap. So we're going to swap I and the value of largest with each other, right? So we're just going to swap those two values. And then much like the heapify that we had before, we once again repeat the process with the largest value. So basically all we're doing here is we start with a node, we check its left and right children, and we say, are any of them bigger than the parent? And if they are bigger than the parent, we take the one that's bigger, we swap it with the parent, and then we repeat the process again, swapping until the largest value ends up at the top of our actual heap itself. So that's the idea of how we actually do this removal, right? Now let me show you what actually ends up happening when we do this removal, right? So I have this heap right here. Let's do a remove on the heap, and let's just see what ends up getting returned back, right? If everything works out properly, we should see that 40 gets returned back. And if I print out the value of my heap, what you'll see is that the heap then has these different values here. And what I can actually see here is that it looks like it didn't quite swap properly, right? So let's just make sure that we've got everything put together okay. I think in this case, basically, I've just probably messed up my heapify. So we do LR. L is less than or equal to the length of self.heap. Let's just double check over these details here. That the rate is greater than, oh, sorry, this should be greater than largest, right? So basically the main mistake here was just that when we're doing these comparisons, basically I set the largest here to be either the left or I should be comparing to the largest again, rather than comparing to the original value. Otherwise, if L was the largest, this would overwrite it. We'd end up with R as the largest instead, which wouldn't be correct. That's what ended up happening there. And we can see that now that I've corrected that, 30 becomes the new top. And that's exactly what we expected. And we could just kind of play around with this a bit more and just do like a few more removes. It's just good to kind of test these things out. You see we get 40, 30, 20, and then the last one here is 10. Now what you'll notice here is actually that we get all of our data back in sorted order, right? So I can insert an array in any sort of ordering, and I can end up with the results in sorted order just by removing all the values off of the heap. This is a really useful property for a heap, and it's one that we're going to take advantage of for our next sort of mini data structure, which is known as a priority queue, which is a queue that stores data in a priority order. So that's what we're going to take a look at in the next video. Thanks so much for watching, and I'll see you in the next one.